Hello, this is the final project presentation for Ashwin Raju and Eric Hartman for ECEE 352 in winter 2014 at Drexel University. So here's a brief overview of what's to come in this presentation. We'll start by stating our objectives and the goals that we aimed for, and then we will go into the design process itself, spelling out some of the details for the preamplifier that was part of this project, as well as the power amplifier, and then talk about some of the feedback that we needed to add to the overall schematic. And then we will look at the result. We'll show a demonstration using some videos that show the wide frequency that this amplifier is able to work at. And then we'll analyze the results and then talk about some of the errors that we encountered and ways to improve this project. The primary goal of this project was to create an audio amplifier that is capable of clearly amplifying a small audio signal to be heard through an 8-ohm speaker. This amplifier had to have a very clear audio amplification that could cover the audible frequency ranges of 20 Hz to 20 kHz. We'll start with an overall big picture of the schematic. As seen, the input from the mic was simulated using a AC signal source, and the resistance that would be provided by the mic is simulated using our SIG. And this schematic can further be broken down into smaller parts. The bigger parts are the preamplifier and the power amplifier. Shown on screen is the preamplifier portion of the schematic. We'll talk about this in detail in coming slides. And this is the power amplifier stage of the schematic, which includes a Darlington pair, a BJT for common emitter amplification, and some feedback components. Now, we'll talk specifically about the preamplifier. The preamplifier consisted of a JFET and a BJT, and we'll talk about each of these and why both of them were necessary.
Okay, so for the JFET part of the preamplifier, first mention why we use JFET, and the reason for that is it has good frequency response characteristics across the range we're looking at. 20 to 20,000 hertz, and it also has a very large input impedance, so it doesn't need to draw current. So here we set our input impedance by the gate resistor to 1 mega ohm, and this means that for signal sources with any output resistance less than 100,000 ohms, we won't see very much at all loading effect, and our source falls into that less than 100,000 ohms, so we're good there. A little bit about the configuration we used. We threw in a source degeneration resistor in order to remove the dependence of the JFET's gain on the actual device's transconductance. And this is good because the individual devices can vary widely in their parameters, like the pinch-off voltage, for example. And finally, we selected the output impedance as 5.1 kilo ohms. So we chose a 5.1K resistor in order to get the gain we wanted to be about 2 volts per volt. But we could do better in this choice because, as it is, this isn't matched very well to the input resistance of the BJT part of the preamp. We'll get to that later, but it comes in at a little bit less than a kilo ohm. So there's some loading here which reduces the overall gain. Now for the BJT stage of the preamp, well, first we should note that the input impedance is fairly low, which is not great for loading effect on the JFET stage, but it's necessary to get a good gain out of this BJT. So we used a common emitter amplifier configuration to get high amplification, and first we biased it so that IC was 3 milliamps in that range, which gives us GM at around 111 milliamps per volt. This leads to our gain being transconductance times the output the resistance at the output. So since our RL further down the line is about 5K, this in parallel with collector resistor gives us about 185 volts per volt of gain. Now, a little bit more about the biasing. Here we actually wanted to get about 30% of VCC across RE. So that way this was to control the base. And then from that, we use that to control the voltage at the emitter. Knowing the voltage of the emitter, we tuned RE to get the desired IE, and then which is about equal to IC. Now the output resistance of this configuration is 2.5 kilo ohms. That's all right because we have a 5 kilo ohm load to this stage, so we don't have any problems with that loading effect. We could also have made some decisions about RC based on the total amount of output swing we could allow. As is, with IC being 3 milliamps and RC being 2.5K, that gives us about 7.25 volts of room between mid zero level AC signal and VCC, where it would saturate, and we wouldn't get any higher than that. So it's possible we could have chosen RC to be higher to give us more room. That's a consideration we make in the future. Okay, so to finish up the preamp, we have to combine both stages, the JFET and the BJT part. And once we do that, we have to take into account the resistance matching between the output of the JFET and the input of the BJT. This matching is not great, so it lowers our gain a little bit, but overall we get a total gain of about 70 volts per volt, which is high enough that we can use a feedback resistor to give us a more stable gain amount. And so we used a 30K resistor to get the gain we need. Okay, so our power amp stage starts off with another BJT common emitter amplifier. We biased this one very similar to the one in the preamp, although this time we chose IC to be about 2 milliamps. Lower IC gives us a larger RPi, so that solves some issues with impedance matching at the input. And we also used an emitter degeneration resistor here so that we could get a more stable but smaller gain out of this section going into the Darlington pair.
The next part of the power amplifier was the Darlington pair. The Darlington pair consists of two Darlingtons, each set up in a common emitter setup. As you can see, one of them is an NPN, which is labeled Q4 in the schematic on screen, and one of them is a PNP labeled Q5 in the schematic. The Darlington pair allows us to have voltage matching between the input and the output, but instead of having a large output resistance, now we have very, very low output resistance on the order of a couple of ohms. The end result of this is that we get a very large current gain, which is needed so that the speaker can properly output sound. This output resistance that I talked about comes from the parallel combination of the resistance into each Darlington that each of the emitters see, plus the small resistance added by the degeneration resistors. A small word on the degeneration resistors themselves. The reason that to use these degeneration resistors is that they add a small negative feedback component to the temperature dependence of the BJTs. This is needed because this helps counter any thermal runaway effects that BJTs can go through. Thermal runaway happens when the BJTs heat up and thus let more current, leading to a higher leakage current, which then consequently increases the heat more, which then leads to even more current. And this is a constant cycle that just keeps happening until something in the circuit breaks. Having the degeneration resistors there helps us counter this effect. The penalty that we get because of this is that there's going to be a small increase in the output impedance, but it's still a fairly small output impedance on the order that's less than 8 ohms. So this penalty really becomes not very consequential. Now, the need for two of these Darlingtons comes from the fact that these Darlingtons themselves are made of smaller BJTs. And as we know, BJTs will only conduct for half the cycle, as a negative bias between VBE will cut them off. This means that there needs to be a Darlington for the positive cycle, another one for the negative cycle. In this case, Q4, the NPN transistor is meant for the positive cycle, and Q5 acts as the transistor for the negative cycle. Another consequence of the fact that these Darlingtons are made of BJTs is the fact that we have crossover distortion. Crossover distortion is illustrated by the PSpice simulation graph that is also shown on screen. When the input is close to 0, that is less than the required VBE threshold, we will get some clipping of the signal, which is why the region that is close to 0 looks approximately like a flat line on the output, which is shown in red in this graph. The reason for this is that since these Darlingtons are made of BJTs, and that BJTs need at least a bias of 0.7 volts between its base and emitter, the BJTs will not let through current until that happens. The way to fix this is to to force a constant DC bias between the two bases of the Darlingtons. Now, since these Darlingtons consist of multiple BJTs, each Darlington needs a 1.4 volt bias at its base to be constantly on, which means that between the two Darlington bases, we need a total of 2.8 volt bias. The absence of this bias will cause some audible clipping in the signal. And the way that we applied this DC bias was through the use of a VBE multiplier.
And one more word about connecting the Darlingtons to the load resistance. Here we used a very large capacitor compared to all of our other ones. This is because here the equivalent resistance seen by the capacitor is lowest. It only sees the couple ohms from the Darlingtons and the load, which is 8 ohms. This drives the threshold frequency very low unless we compensate by using a higher capacitor.
This bias of 2.8 volts was achieved through the use of a VBE multiplier. A VBE multiplier is simply a BJT with resistors connected to its base that is then also connected to the collector and emitter respectively. The schematic on screen shows the VBE multiplier that we used. In order to calculate the values for R7 and R6, we are going to once again assume that IB that is flowing through this BJT is comparatively very, very small. Now, if this is true, then we know that most of the current that comes through R7 and R6 simply pass through R7 and R6. In this case, R7 and R6 then effectively work as voltage dividers. Specifically, the voltage across R6, which in this case is also the voltage that is equal to VBE of the BJT, is then simply VCE times R6 divided by R6 plus R7. Rearranging this equation, we can get that R7 over R6 plus 1 times VBE equals VCE. Now, since this is in fact a BJT, we know that the VBE is going to be 0.7 volts in normal active mode, which is what we wanted to work at. And therefore, R7 over R6 needs to have a ratio of 3, so that 3 plus 1, which is equal to 4, times VBE can equal the 2.8 volts that we need between the two Darlington bases. So that concludes the building stages of the schematic part. Now, what we did after this is to simulate this schematic in PSpice to look at the range of frequencies that this amplifier can handle very well. Shown on screen is the output from the preamplifier as well as the final output. The red line shows the output from the preamplifier, which was able to amplify the signal up to about 22 decibels. And the green one shows the output from the power amplifier, which we ended up getting about a 31 decibel gain when it's at its full capacity, which is well beyond what we were expected to do. As you can see, even though the amplification is very good and exactly where we wanted it to be, the frequency coverage isn't as good as we would like to be. For instance, the negative 3 dB point seems to be right around 300 hertz, which is a little higher than we were hoping for. And this, in fact, will cause some issues, and we'll talk about it in a later stage. Shown on screen is the result of a transient response analysis done via PSpice of the schematic that we've talked about so far. In green is the input signal coming from the mic. In purple is the output of the preamplifier. And in red is the output of the whole amplifier. As can be seen, the amplifier was able to amplify the green signal enough that it should theoretically come out of a speaker and be audible in the frequency ranges that we talked about. As you can also see from the graph, the output gain was about approximately around 40 volts per volt, which is very good, and this is exactly what we expected it to be. And as you can also see, it's also evident that there's no crossover distortion in the circuit anymore due to the VBE bias that we put into place. So based on this knowledge, we decided that we would proceed to the construction of the circuit using breadboards and physical equipment. And during that process, we learned that simulations and real-life scenarios don't always match up exactly one-to-one.
So there were some issues with the construction of our circuit. As you could see, the simulation said, okay, it works. But when we built it, issues came up. So the main method of fixing these was to tweak resistors using our knowledge of what we expect the circuit to be doing, and try and hone in our values more on what would be ideal for what we're expecting each section of the amplifier to be doing. So in practice, this meant going through most of the resistors, looking at what they're for, and trying to adjust their values higher, lower, seeing what was happening, and using that to confirm or deny what we thought the circuit was doing compared to what it was, expected to do based on our simulation and calculation. This included checking the capacitors as well. But to experiment, we took the bootstrap capacitor out, and the circuit actually seemed to work better without it. Probably because our circuit had open loop gain that was decently around where we wanted it to be, so we didn't have to introduce this feedback in. And in this case, this is actually a pro, because bootstrap capacitors tend to make the system more nonlinear and noisy. So since ours worked fine without it, we decided to keep it that way.
So at this point, we've talked about all the different stages of the amplifier. What's a better way to test an amplifier than to play some music through it? So right now we're going to show some sample output from the physical circuit that we built out of this schematic. Waiting for someone to run by, but what the hell are you guys doing? Now, as you've heard, the amplifier was functioning very well through a wide variety of frequencies and a wide variety of pitches. and a wide variety of songs. Since the goals for this project were to produce a very good amplifier, I think in that sense we can say that the project was a success. However, that's not to say that there weren't issues with it. For instance, here are some samples that kind of underscore the issues that the amplifier will have.
This is the end. Hold your breath and count to 10. Feel the earth move and then hear my heart burst again. For this is the end.
As you might have seen, there's still some improvement that we could do for this amplifier. After going through the design phase, now we are able to see these more clearly. The main issue is, as you can tell from Adele, we get some distortion when there's a range of high and low frequencies in our song, and that's because our low frequency cutoff is still fairly high. It's still in the audible range. So we play a song, starts off with a low frequency, so we turn the volume to a setting that's good for that. But when the song progresses to a higher frequency, our amplification has gone up. So now we're getting like maybe 6 more decibels, which is twice as high for an increase of 1 octave. Regardless, we get a lot more amplification at a little bit higher frequencies. And so this causes our circuit to go into distortion. So there's probably 2 solutions we can make for this. The first is the most direct, and that's to change the frequency response a little bit. That way we include more of the low frequency set, so we don't have this problem of it works in the lower part of the song but not in the higher part. And our second change would be to give more room for output swing in the design of the amplifier, meaning that we don't saturate to VCC or ground as easily when we go to high amplitude signals.
So as Eric was saying, if we were to improve this project in the future, we would take care of the issues with having multiple frequencies in the same song that are ranging from a very low to a very high frequency, where we have to manually go in and change the volume because the amplification is too high and the speaker distorts. Other than that, that's it for the project. We hope you've enjoyed this presentation and have a very nice break.